So, welcome to this course titled Advanced Microwave Guided Structures and Analysis. Myself Professor Bratin Ghosh from the Department of Electronics and Electrical Communication Engineering, IIT Kharagpur. So, this course is essentially targeted towards analytical methods for the for the investigation of guided structures in general. We will start the course from the scattering matrix concepts. We would walk through the unitary properties of the scattering matrix, the basics of the scattering matrix concepts. Then we would go to the instantaneous form of Maxwell's equations. So, the treatment of the Maxwell's equations here is going to be different from other undergraduate treatment in the sense that we are going to follow the textbook of Roger F. Harrington, which is a standard text we follow here at the postgraduate level. So, we are going to deal with the instantaneous form of Maxwell's equations, particularly its differential and integral forms for the point source and for within Maxwell's equations within a region. We are going to graduate to the generalized current concept and also interpret the conservation of power. We will evaluate the Poynting vector and interpret it from the point of view of conservation of power. The different terms of the conservation of power, how does it lead to the comprehensive understanding of a radiating structure. Next, we are going to understand the time harmonic form of Maxwell's equations. This is very important because this directly leads to the concept of input reactance of any kind of radiating structures or input reactance of any excitation source immersed in a rectangular waveguide or any kind of waveguide for that matter. How does the radiated power and how does the complex power radiated by the excitation source link up with the input reactance, with the input impedance, leads to the a deeper understanding of the matching problem, okay, and the coupling problem in general. Okay. What is the difference between the real part of the radiated power and the imaginary part of the Poynting vector? How do they all fit together in the conservation of power? This is very important from a fundamental understanding towards any kind of radiating structures or, as I said, excitation schemes immersed in any kind of guided structures. Then we are going to go to the solution of the wave equation in a homogeneous medium without the source. We are going to begin the source free problem and then graduate to the insertion of an electric current source inside a homogeneous medium. We are going to see that for the insertion of an electric source in the homogeneous medium, we need to invoke something called a vector potential, which will enable us to calculate the electric and magnetic fields. We are going to also meet the Helmholtz equation and we are going to discuss its particular significance in electromagnetics, because it is a very central point in electromagnetics, which is the beginning of all advanced Green's function techniques. We are next going to treat the magnetic current source and illustrate first of all its relevance in electromagnetics. Okay. So, though the magnetic current source does not exist in reality, we are going to discover that it is as important in electromagnetics as an electric current source. Okay. Its relevance to the computation of the Green's function for slot coupled problem, without which we cannot walk a single step in the analysis of a slot coupled problem. The dissociation of the two problems which are slot coupled by the insertion of a magnetic current source. So, which enables us to get a strong foothold to the slot coupled problem in general. Then we are going to move on to the rectangular waveguide. Our understanding of the potential functions and how to calculate the fields from the potential functions would enable us to directly use those concepts in the first kind of boundary conditions, which is a simple boundary condition of the rectangular waveguide. But the same principle is used for more advanced concepts like antennas or dielectric structures, where the boundary conditions are much more complex than the rectangular waveguide. Okay. So, though the mathematics is quite a bit complex there, the starting point is the use of the potential functions and applying it to find the modes in the rectangular waveguide. So, we are again going to visit the concepts of cutoff frequency, the dominant mode and the propagation and attenuation constants inside the waveguide. We are also going to investigate the characteristic impedances of the TE and TM2Z modes in the waveguide, and we are going to see that the characteristic impedance is not unique because of the presence of the boundary condition in the waveguide. Okay. We are going to again we are going to also calculate the power flow inside the waveguide, particularly the power flow in terms of the modes in the waveguide, and also compute the power dissipation on the waveguide walls. This is particularly significant and very significant for the next part of the problem, which is the rectangular cavity resonator. A rectangular cavity resonator is used everywhere as a backing structure for antennas to improve its front to back ratio. It can be used to excite dual resonances in antennas. One resonance can be due to the antenna, or the other resonance can be due to the cavity structure. It can be used also as a matching structure to enhance the matching to the antenna. So, the idea behind a rectangular cavity resonator is a very fundamental idea, and its analysis is extremely important, because unless we understand the cavity resonator, we will not be able to use it properly, we will not be able to know how to excite a cavity resonator effectively and how to couple it with an antenna structure. So, therefore, the understanding of the potential functions of the TE to Z and the TM to Z modes of the cavity and the resonant frequencies of the cavity, and particularly its quality factor, the stored energy and the quality factor. Then we are going to move to a very important concept, which is the reciprocity theorem. We will investigate the reciprocity theorem, prove the reciprocity theorem, use the reciprocity theorem next in order to calculate the amplitude of the nth propagating harmonic from an infinite spectrum of waveguide harmonics for the case of a current source, both an electric current source and a magnetic current source radiating inside a rectangular waveguide, because they will radiate in general an infinite number of harmonics both in the forward direction and the backward direction. The central problem is here is to find out the amplitude of one given nth order harmonic propagating in the forward and propagating in the backward direction, both for an electric and a magnetic current source. This is vitally important because the same concept is used for any class of antenna problems to find its input impedance, to find the fields inside the antenna and near to the antenna, okay, and to find and evaluate the Green's functions for a source immersed in any kind of antenna structures, be it be the microstrip patch or be it be the dielectric resonator or any kind of antenna. Okay. So, the starting point is the evaluation of the modes from an infinite spectrum of modes within a boundary value problem. So, therefore, the reciprocity theorem and its analysis inside the waveguide is going to give you a very important starting and stepping stone towards the treatment of more advanced problems. And it is vitally important because it is used everywhere in electromagnetics. Okay. Then next we will come to the analysis of the guided structures, more advanced guided structures, particularly the partially filled rectangular waveguide, for which the T to Z or the TM to Z modes for the homogeneous waveguide are no longer valid because of the presence of the dielectric strip. We are going to investigate alternate mode functions which will enable us to evaluate the modes of such structures. Okay. Then we are going to move to the dielectric slab guide, which is an extremely important structure because all planar structures, namely the microstrip patch or any kind of slot, okay, which are resident on planar structures, ultimately for good physical understanding of such structures, we need to know what is going on inside the substrate. How to calculate the propagation constant of waves inside the substrate, what are the mathematical expressions of the fields inside the substrate, and what is going on outside the substrate. So, we need to know that, we need to know the cutoff conditions for the dielectric substrate. Unless we have a deeper insight into the substrate, we will not have any physical understanding of the substrate. We frequently do an HFSS simulation of microstrip antennas or some such antennas, but doing simulation only does not give any kind of insight into what is going on inside the structure in general. That is why we study electromagnetics. While simulation is an important aid to our study of electromagnetics, this does not at all replace the mathematical tools or the mathematical building blocks for electromagnetics, because it does not yield any insight as to what is going on inside what is going on in the structure. So, then we will go to cylindrical wave functions. The cylindrical wave function is again a very important foundation stone for the analysis of the, first of all, the cylindrical or the circular waveguide. We will study the circular waveguide, its cutoff frequency, propagation constant, and again graduate to the circular cavity. Okay. We are going to find the modes inside the cavity, and it may also be remarked that here that it is a very important starting point also for the analysis of more advanced structures, which are cylindrical dielectric structures, which the analysis of which is done through the well known Sommerfeld integral. Well, we cannot go to the cylindrical dielectric structures because it is a huge area of research, and it is you know, like its area of work and its depth and expanse is too big to be covered in this kind of a lecture like this. But again, the concepts earned by the application of the cylindrical wave functions to the circular waveguide or the cylindrical waveguide can be directly enhanced to have a deeper understanding of dielectric cylindrical structures, for which we use, as I said, more advanced integral representations like the Sommerfeld integration. We are next going to illustrate the coupling problem, which is a very important problem practically for the coupling of any kind of antenna structures to a guided structure, particularly the aperture coupled structures, the probe coupled structures, and the waveguide coupled structures. So, we are going to illustrate how the aperture coupled structures might be different from probe coupled structures, shows through some representative examples how does such coupled structures work to have a you know, like a more hands on practice or a hands on session, I mean through lectures, how the concepts we study in the rest of the course, they all fit in to give us a more comprehensive idea towards the coupling problem. Hopefully, this course is going to be a very interesting course and a very insightful course. We will all understand a lot of things from this course, and we can move on in our own different directions from this course, namely the planar problem, the waveguide problem, a rigorous treatment of the waveguide problem, a rigorous treatment of non-TEM waveguides, okay. The treatment of cylindrical wave functions and the treatment of the coupling problem. They are all starting points of big areas of work in the literature. So, I think this course is going to be a lot of benefit to all practitioners in the field of electromagnetics, faculties of engineering institutes, engineering colleges, research scholars, graduate and undergraduate students, in the field of electromagnetics, in applied electromagnetics, and people working in the industry at all levels. Okay. People from the public sector, from the private sector, we will I think will benefit a lot from this kind of course. Okay. So, thanks.